learning decision tree is one thing, but how to learn it in a good way, we need cross-validation. You're convinced why we need that, because we want to touch every data point, give a chance. We want to give the chance of being tested to every data point. So we do this cross-validation. And we avoid peeking into the data through test data to keep some part of the data as future. So we never know what is in the future. And how do we measure what is good, what is bad? We are going to learn many matrices, but in case of classification, we look at accuracy. In case of regression, we look at some kind of difference between actual and predicted value. Now, the thing is that on x-axis is the number of examples that we have in our training set. So the more examples we use in the restaurant data set, the better we have the performance. So few examples, we have more mistakes. The more the number of examples, the higher the performance is, accuracy or whatever we try to use. As I explained, if we have 100 examples, this is not the best policy to use all to train our any algorithm, not only decision tree. If we use all examples, one big risk is that the algorithm will memorize training data and will give very good performance, but in future on test data, it will fail terribly. So this curve is used in textbooks to explain why the performance measured on y-axis in terms of accuracy and the size of the tree that if we use all the data, all the attributes in the data, the size will grow. So 10 nodes, 20, 30, up to 100 nodes. Up to 100 nodes means every example in the training data has a branch in the tree. So that will cause the accuracy to go up for training, but go down for test. And they diverge. The more the size of the tree, the bigger the difference between test and training will be. So we want to find a sweet spot where the tree is concise. It's not too much complicated. It's not using all of the examples and all of the attributes, but best possible and provides good enough accuracy in balance between test and training. Now, this is textbook, right? So we, in practice, never know where do this line go because we don't have access to the future data. That's why we split into train and test. And if we plot this error with respect to the decision tree, for most of the problems, you will see this divergence. And this is called the problem of overfitting. The higher the training error goes, the algorithm or the decision tree is memorizing, overfitting to the examples and becoming less and less generalizable for the test data. It's just like, even if we add in some random attributes, for example here, to predict the result of a rolling a die, we add day of the week, month of the week, and color of the die, which has no correlation or no connection with the result of the die, if it's fair, then we put in these three variables and the decision tree can somehow learn, add these variables from the training examples and get misled. So in future, we know these don't have any implication on the result of the die, but they will be incorporated into the decision tree or any other algorithm, and we are set then for problems. So overfitting onto irrelevant variables is one cause of that divergence. And the next textbook graph for the same concept that I want to show you. On x-axis, we have size of the tree, number of nodes in a tree, and on y-axis, we have error rate. The higher the size of the tree is, the lower the training set. And at some point, we see that the error starts increasing for test set, and we want to test that sweet spot somehow. Optimal tree size, maybe 6 or 7 nodes. Less than that, we are underfit. Beyond that point, we are overfit. Now, other than these irrelevant variables and size of the tree or number of examples that we use to induce a tree, there can be some problems that we want to avoid. For example, one problem is same example in both classes. Noisy data, right? Same example, all attributes, same values, class 1, same values for class 2. That is not possible, right? That must be an error, noisy data. But if we keep increasing the size of the tree and keep feeding all the examples to the data, as many as we have, the tree will get overfit to those examples and produce erroneous results in future. Similarly, there can be noise in the attribute values as well. Not only the confusion between the class labels, but the attribute values can be recorded incorrectly. So accepting the fact that there will be noise in the data, we don't want to train too much, too long, using all the information we have, increase the tree size as much as possible. It's a guaranteed way to overfit. So that's why avoiding overfitting has many reasons: to avoid the noisy data, to avoid the mislabeling problem, and to have a concise hypothesis, not too big, not too small. So in conclusion, when the instances can be represented into attribute value pairs, we are good to choose decision tree. It is mostly if the dependent variable is having discrete values, decision tree is a good option. But if it is having numeric values, continuous variable, we can still use decision tree. We refer to those decision trees as regression trees. And concise term is CART, classification and regression trees. Whatever is the dependent variable, decision tree will work. But I will leave it to your imagination how a classification tree can solve regression problem. You just need to think about the leaf node. In the leaf node, in classification, we are getting discrete items. But in regression problem, the leaf node will have a range of numbers. And we can take an average of those numbers and output the average as a regression output. Or we can fit a regression inside the leaf, regression solution inside the leaf node for all the data points, and use that regression solution to output Y. So it's robust to noisy data, and we use in machine learning a term Occam's razor. That means we don't use a more complex representation to explain or communicate a concept that can be communicated with simpler representation. The first thing that you do to solve a problem, classification problem, is a decision tree, because it does outperform human experts, and it is fast to build. It is simple to implement, like to deploy on the cloud, and it's human readable. So you induce a decision tree, and then a domain expert can verify, yes, this decision tree is according to the complexity of the problem, and the variables and decision variables are having good decision factors. And even in newspapers, you often see decision trees being published for common people. And they are being used in many commercial products. And they do have some downsides. Number one, each node will handle one variable at a time. We live in a multivariate world, right? So this is one limitation, too naive for the real complex problems. And large decision trees can be produced, and they will be hard to understand by us. And finally, for a decision tree, for learning a decision tree, we need to have a data that is of tabular shape, structure. So fixed length feature vectors is the prerequisite. And we have to have all the data. Only then we can learn. We will see some problems where we can apply algorithms that learn on the fly. As the examples come, we update the algorithm, and it learns incrementally, stochastically. The decision tree is a batch mode learning method where we need to have all the data first in place, and then we learn. If new data comes in, we will create a new tree. The old one will be discarded.